Hello, let's make Asteroids.
Asteroids is a game where you control a small spaceship that floats around in space, and it follows all of the physics you would expect to see in space. And you can thrust the ship and rotate the ship, and you shoot bullets to try and break up the asteroids. If you hit an asteroid, it's game over, it starts again. And if you manage to clear the screen of all the asteroids, which admittedly in my version of it here is actually not very difficult to do, he says, firing aimlessly all over the screen, then you get 2 more asteroids to shoot at, guaranteed not to appear where the player is, and your score increases. And it's really about how long can we survive.
When I started this project, I expected it to be quite simple. I was going to use some sprites for the asteroids and just move them around on the screen. However, it quickly became apparent that was rubbish, and so I decided to go back to how the original was done and implement a vector graphics framework. And this means I have to give a little warning up front. There's going to be some mathematics in this video. You often hear people say that to be good at programming you need to be good at mathematics, and I don't think this is necessarily true. In fact, I think the majority of programming actually involves rather trivial mathematics, or here in the UK we would call them simple sums. But if you're going to do games with slightly more advanced 2D graphics or full-on 3D graphics, you're going to have to know the mathematics behind it. There's no getting away from it. But, and with this video I hope to show, with a simple toolkit of maths, you can achieve quite cool things. Let's get started.
As you'll be well aware by now, I'm currently using the One Lone Coder game engine for pretty much everything. This allows me to do graphics and input in the console, at the command line. So here I've inherited from the console game engine, and we typically override the 2 functions onUserCreate and onUserUpdate. This one updates the screen, and this one is called when the application launches. And at the moment, all the onUserUpdate does, per frame, is clear the screen. It fills it full of black pixels. In my int main, I create an instance of the game engine, and in this case I've set it to 160 characters wide by 100 characters tall, and each character is 8 by 8 pixels.
Asteroids only contain simple objects, the ship, and the asteroids, and these are things that float around in space. So I think we'll create a struct to represent these objects.
So let's create a simple struct, and we'll call it spaceObject. And this object contains some simple properties. Firstly, x and y coordinates for its position, i.e. where it is in space. And we'll also include some velocity coordinates, and we'll come back to that in a minute. So this will be the speed and direction that the object is travelling in. I also know that most of my objects are going to be asteroids, and they change in size, so I'm going to store that here too. I've got different types of objects in the game, so I'm going to collect them together in vectors. So this vector is going to store the asteroids. For now, let's populate this vector with a single asteroid. I'm just going to use the initializer list to do this. So I know that this is cheating a little bit, but I know that the format of my struct is such that the first element is the x position, so I'm going to say that that's 20, and I know that the y is the next one. We'll choose some velocities, let's say 8 and -6, so this is how much it changes per frame, modulated by f elapsed time of course. And finally we've got the size, which I'm going to force it to say I'm an int. That'll allow the initializer list to compile properly.
If we didn't tell it was an integer, it might think it's a short or a char or something else.
Let's take a minute to do a very brief kinematics reminder, i.e. the study of very simple motion. We know that at any given time an object is at position p. If an object changes position, let's say it moves to p2, which is a new position, from an old position, that's got to take time. And that, of course, gives us velocity. In much the same way, we can think about acceleration, because if we've got a change in velocity, that too is also with respect to time. It goes without saying then that if we know our original velocity, the time that's passed, and our acceleration, we can calculate our new velocity, which in this case becomes v2 equals a multiplied by time plus v1. And the same applies for our velocity. We know that our new position, p2, equals the velocity times time plus the original position. we'll use these very simple equations to update the position of our objects on the screen. But let's not forget that P is actually an X and a Y coordinate, and so therefore V and A must also be directional. They need to be vectors. I'm going to update and draw the asteroids at the same time. And I'm going to use a little for loop to iterate through the vector. So using the equations we've just done, we know that the x position of the asteroid needs to be updated by the velocity vector times the elapsed time.
And don't forget that this f elapsed time variable is the update between successive frames. It's the time taken between one frame and the next. And that allows us to run the program at a known speed across a variety of different computing systems.
I've just spotted error number 1. I've put this in the onUserCreate function. That's no good. We need to do this on the on-screen update. We do exactly the same for the y coordinate. In fact, there won't be any situations where we're updating just x or y on its own. We'll always be doing things in pairs. To see if the motion is sensible, I'm going to draw the asteroid as a rectangle for the time being. So I'm just going to iterate through x's and y's according to the size of the asteroid. And I'll use the draw function to draw a pixel at these locations. Let's take a look. So we can see my asteroid drifting through space, and oh, it's gone off the screen and we'll never see it again.
And this is the first part that makes Asteroids quite a challenging game to make. We want all of our space objects to wrap around the screen, which means we need to think about how we map information to the screen.
Currently our screen is just set up as a standard two-dimensional array. It's a grid of pixels. But when we want an object to go off the edge of the screen, we want it to appear on the other side. So we need to wrap it all the way around and bring it back. So if we create a system where we know that this edge is actually the same as this edge, we can start by drawing that edge, and we know that we need to wrap around like this. And in fact, it looks like a cylinder. And this can be implemented by whenever we go beyond the screen width, which would happen to be on this side, we reset to 0. But it gets a bit more complicated, because we also want to wrap in this direction. We want anything that goes over the top to also loop back round to the bottom. And it may be tempting to think that we're treating this as some sort of sphere. But we're not, because a sphere can't maintain a standard coordinate system. You've got to have some distortion as you go around it. So as you can see at the top and bottom of the sphere, all of the pixels get very close together. And as we go around the sphere around its equator, we get larger pixels. So this is a distortion. And in fact, if you want to wrap a 2D array around both its x and y axis, you need a torus, or a toroidal mapping.
Looks a bit like a donut.
And with this mapping, we've got equal spacing going around that way, and equal spacing going around that way. I've got a feeling we're going to need a mapping like this quite a bit for this game, so I'm going to create a function which takes a set of coordinates and wraps them around using a toroidal mapping. I'm going to call it wrap coordinates. And it's going to take an x and a y as an input, we'll call those ix and iy. And it's going to output ox and oy. So the first thing I want to do is set the output to the input. And then I want to check if the input is beyond the boundaries of our array. So let's take the x-axis first. So if the input x is less than 0, then I want to adjust my output to be the input x plus the current screen width. which is an integer. That's why I've casted it to a float. So let's say ix is -5, we end up setting the output to being screen width -5, so it goes to the other side of the screen. Likewise, we can go checking if the input x is greater than screen width. Then we update the output again. Naturally, it's exactly the same for the y-coordinate, except instead of screen widths, we want screen heights. Now we've got a function that will create the toroidal mapping, we can always update our space objects to make sure that they stay within the game space. It's just a case of passing the current position, x and y, into the function, and we get them back. So it looks a bit strange, this, but it's valid. Let's take a look. So we can see our asteroid now drifting off one side of the screen, and it's appeared on the other. But there was a slightly undesirable artifact there. Let's see it again when it goes off this edge of the screen. We know that our rectangle is referenced from the top left, so we don't see the top right of the rectangle appear on the other side.
And this is because even though our objects can be wrapped around using this coordinate mapping system, the graphics routines in the console game engine can't. They're not aware of it. They don't know that they should wrap around. So we're going to use some polymorphism to our advantage.
In the console game engine, all of the drawing functions ultimately call the draw function, and this plots a single pixel to the screen. So what I intend to do is to override this draw function to take advantage of our new coordinate system. But I need to make one change to the console game engine here. I'm going to say that this method is virtual. Since I'm going to override it, I'm just going to copy from here and create a new function in our new class underneath the wrap coordinates. Now we've overridden the draw function, we need to use our wrap coordinates function. So I'm going to create some temporary variables, fx and fy, and I'm going to use our wrap coordinates to take the requested inputs, the x and y, so this is wherever the drawing routines want to draw the pixel on the screen. I'm going to generate the new fx and fy, which are the wrapped coordinates. And then I can call the original draw function, so not the one we've just overridden, with the new coordinates.
And if you've ever needed an argument for object-oriented programming, this is it.
With just this very simple change, we've now changed the nature of some fundamental parts of our drawing engine. So as we can see, the rectangle goes off the screen, but it draws appropriately at the bottom. We'll see again as it's going across. So the drawing routine wraps around automatically.
And so this has given us two different spaces. One is game space, which contains the asteroids and the ship, and they're having the central coordinates wrapped around. And the other is the screen space, which is also using the wrap coordinates function. The two are separate, and we'll be doing all of the collision detection and actual game engine in game space, and all of the rendering happens in screen space.
Now it's time to start thinking about how we add the player. We know that the player controls a spaceship that can be rotated. And so one property we need to store for the player is the angle of rotation. We also know that the user applies thrust, and so this adds acceleration in the direction the ship is facing.
In space, nothing slows the ship down. That's why it drifts across space. So in order to slow the ship down, you've got to turn it around the other way and apply thrust, like a brake. And it's this that makes the game quite challenging.
Since it looks like angles are important, I'm going to add them to the space object. And so we'll also have to update our asteroid initializer. We'll just set the angle to that, to 0. And we'll create another space object, which is the player. In the onUserCreate function, I'll initialize the player to be in the middle of the screen with no velocity and no angle. Now in quite a few other of my videos you'll have seen me use sine and cos quite a bit, but I thought it'd be useful to understand why. So let's assume I have an angle, theta, and I want to work out a vector related to that angle. Let's have a look on an axis. So we've got y in that direction, x here, and we've got some vector to that point, and we've got this angle. Well, let's simplify it for a moment and assume that our angle is 0 degrees. Therefore, on our axis, we know that our point lies somewhere on the y-axis. So we can see it has actually no component in the x, and we know that sine of 0 degrees equals 0. And cos of 0 degrees equals 1. If we take a point along the other axis, this time we know that our angle must be 90 degrees. So we'll change those from 90s. Sine of 90 degrees is of course 1, and cos of 90 degrees is of course 0. And these two functions are great because they will give you a circular line between the 2 points. And in fact, it keeps going round and draws a full circle. With just these functions, it generates a circle with a radius of 1, which means that if we treat our x and y as components of a vector, we get a unit vector. And this is very useful. Let's add some controls so we can steer the player. So we'll just look at the M keys variable, and if the user is pressing the left key, or holding it down even, then we just want to adjust the angle of the player by a little bit. It's exactly the same for the right, except in the other direction, so the negative becomes a positive. Thrust, however, is a little different. The player will thrust the ship forward if they're holding down the up arrow. But since we don't store thrust as part of our space object, we need to update the velocity instead. So for the x-axis, we're changing the x velocity by sine of the player angle times, and I'm going to pick a number at random here, 20 times f elapsed time. And as we've just seen with the maths, altering stuff in the y-axis uses the cos function. So by doing this, we know that we get a vector related to the angle that the player is pointing in, and we can use that vector as our velocity vector. But there's one little change to make, and that is we've got to add a little minus sign in front of the cos.
And that's because our screen is upside down. 0 is at the top, screen height is at the bottom. That's not how maths works.
So as we learnt earlier, we know that when we change velocities, we're using acceleration, and of course that is what our thrust is. So acceleration changes the velocity with respect to time. And we can use a similar set of equations to now update the position using the change in velocity. So velocity changes the position with respect to time. So I take the player's x-coordinate and update it by its velocity vector that we've just calculated, multiplied by f elapsed time. Let's not forget that our spaceship is also an object floating around in space, so we'll need to wrap its coordinates too, to keep it within the game space. So now we get on to the fun part. How do we draw the ship?
I could represent the ship as another rectangle, but the problem is I don't have any routines to draw a rotated rectangle. Also, it's not very useful. It doesn't tell the player which direction the ship is facing, so he won't know which way the bullets are going to go, and he doesn't know which way the acceleration is going to be applied when he presses the thrust button. Fortunately, and this is becoming a theme with this video, maths can help us out.
Let's consider using an isosceles triangle as the ship, so it's clearly pointing in the pointy direction. We can see that this coordinate is about -0, -5. This point is -2.5, and the y coordinate is 2.5, and this one becomes +2.5, 2.5. Whenever we see 2D coordinates, don't forget we've actually got a vector from the origin. So we've got one vector up there, one vector there, and one vector there. And as we've seen previously, we can use trigonometry to do things to vectors. We don't need to worry about the lines so much, because once we've got the points, we can use the game engine's draw line utility to draw lines between them,
thus giving us the ability to have wireframe objects on the screen.
Once we've got a set of points, we can use matrices to transform them. Now this video isn't going to be a full-on video about how matrices work, but it'll give you enough to get going. I see matrices as just a convenient way of grouping similar equations. So if I have my input points x1 and y1, I want to get an output x2 and y2. I want to do some sort of magical transformation between them. If I want to do nothing, I create what's called an identity matrix, which looks like this. It has all ones in the main diagonal. And you perform this matrix multiplication operation like this. We take this component and multiply it by this component. Then we take this component and multiply it by this component. And finally, we take both of those and add them together. So if I write this out, what this becomes is x2 equals 1 times x1 plus 0 times y1. And it's exactly the same for the second component, the y. 0 gets multiplied by the x1, this 1 gets multiplied by this y1, and these two results get added together to give us y2. So in this case we can see we have 0 x1 plus 1 y1. Ultimately this of course resolves to x2 equals x1 and y2 equals y1. It's boring, but I said it doesn't do anything. This is a null matrix, it does no transformation. That said, if I make a simple change to this matrix, for example, change this 1 and this 1, if we change these to say 3 and 5, then our equations below, the 1's also change to 3 and a 5. And so therefore, in this case, our output, x2, equals 3 times our input for the x, and for y, it equals 5 times the input. In short, we have scaled our original point. And so if we took that scaling matrix and applied it to our points, we get a different size ship. We've scaled by 5 in the y-axis, and these points would become, because we've scaled by 3 in the x-axis, and 5 in the y-axis.
Even though matrices may appear intimidating, don't forget they're just a notation for describing a set of simultaneous equations.
This simple example was of a scaling transform matrix. However, we're not going to scale the ship, but we might want to scale the asteroids later on, so we'll come back to this. What we're more interested in doing is rotating the ship.
Rotation matrices are more complex, and Wikipedia has some excellent resources on how they're derived and how to use them. In fact, it does for all the 2D transformation matrices. But for completeness and for this video, I thought I'd show how I can derive a rotation matrix. Because I feel as a programmer, it's always useful to understand why I'm doing does what it does. So when it goes wrong, I've got more hope of understanding the problem.
Let's assume I've got 2 points, P1 and P2, and I want to rotate P1 to be in the position of P2. This problem becomes challenging because I might not know what the original angle of my point was. All I know is that I want to change it by a small amount. Let's just label these angles so we can keep track of them. We know from earlier that we can represent our points using sine and cos. We'll call that P1x and P1y. Well, we can see in a similar way that P2 is actually the sum of these two angles. So we could write this out as P2x equals cos of angle 1 plus angle 2, and P2y equals sine of angle 1 plus angle 2. Now our problem is we might not know what angle 1 is. All we know is we want to rotate it by angle 2. So we can use some trigonometric identities to help us out.
Remember those from high school?
So when you've got cos and two angles added together, you can also represent that as cos of angle 1 multiplied by cos of angle 2, subtract from that sine of angle 1 multiplied by sine of angle 2. And this is really neat, because here we've got cos of angle 1 is also our original point, and sine of angle 1 is also our original point in the y-axis. So we can rewrite our equation as simply being p2x equals p1x cos angle 2 minus p1y sine angle 2. So now we have a way of creating our new point based on information that we know. We know our existing point's location, we know the angle we want to rotate it by, we know enough to perform the transformation. The y-axis uses a similar approach, but it uses a different identity. When we've got the sine of two added together angles, the identity looks like this. Sine of angle 1 multiplied by cos of angle 2 plus cos of angle 1 multiplied by sine of angle 2. And just as we did before, we can use a very similar approach. We can see that sine of angle 1 is the same as our original point. So knowing that, let's write this one out as well. For p2y equals p1y in this case times cos of angle 2 plus p1x times sine of angle 2. And just as before, we've got all of the information we need to solve this. But if we just swap these around, and we can do this, just so everything is consistent, what we see is we've got a matrix operation. And this is in fact our rotation matrix.
So we've now developed a matrix for scaling an object, we've developed a matrix for rotating an object. There isn't really one in 2D for translating an object, that is moving it across the screen. You just add a vector to the points.
So, why was all that necessary? Well, if we define our ship as a set of 3 points in the triangle, as we saw before, we can use matrix operations to manipulate these points. I'm going to create 2 more arrays to store the transformed points. So the idea here is the model never changes, but what we draw to the screen is the transformation of the model.
And this is how all wireframe graphics work. In fact, it's how all 3D graphics work, even in the most modern of games. If you want to be a games programmer, particularly a modern day games programmer, you're going to need to become familiar with matrices and vectors.
When applying transformation matrices, it's quite important to do it in the right order, or else you'll get odd results. So the first thing I'm going to do is rotate the model. And this assumes it rotates around the origin of the model, which as we saw before was 0, 0. And all this for loop does is go through all of the points in the model and multiplies them, like the matrix versus the vector that we've just seen. But the angle that we want to rotate by is the player angle. So we can rotate the model triangle in the direction the player is facing. Once the model has been rotated, I then need to offset it to where the player currently is. So I need to set it to the player's x and y coordinates. They're the position vector of the spaceship. Once I've rotated and translated, I want to draw it to the screen. So I'll create a loop which goes through all of the points and draws lines between them. You'll see it goes up to points 4. That's because there's one more point here than that in the model. And by using the modulus function in here, I make sure that I get all 3 lines drawn. And don't forget, the draw line routine calls the draw function, which we've already overridden with our wraparound function. Let's see how this all comes together. So I can see a triangle in the middle of the screen, and I'm pressing the arrow keys to rotate it, and I press the up key to apply some thrust, and of course there is no brake in this, so the ship will just carry on drifting, and as it went over the edge of the screen, the draw line routine worked quite satisfactorily.
The thing is, now that we've developed a system for rendering wireframe models, our rectangular asteroids, well, they look a bit rubbish. So let's make those wireframe too.
Because I don't want to repeat this code, I'm going to wrap it up in a function that draws a wireframe model. So the draw wireframe model function takes in a vector of pairs, and these pairs are the x and y coordinates. So we can define a model and give it to this function. And when we draw it, we call a position xy, where on the screen do we want to draw it. We have an angle of rotation, we have a scaling factor, and we have the colour that we want to draw it. And here we can see in the comments that the first element of the pair is the x-coordinate and the second element is the y-coordinate. And the first thing this function does is create another vector to hold the transformed coordinates. We don't want to change the model coordinates each time. They've got to stay static. So I create another vector the same size. And I do the rotation. Then I apply the scaling matrix. Then I translate it. And then I draw the polygon. Exactly the same as we've done before, but now we can draw any kind of model that we want. So all of this original ship drawing code can go now. Bye bye. And instead we'll create a vector of pairs of floats. And we'll call that vec model ship. And we'll define the model in the onUserCreate function by simply using an initializer list. So there it is, there's our spaceship, simple isosceles triangle. So now when we want to draw the ship, we call the draw wireframe model function, send it the model, the offset, where it is in space, and the angle of rotation. Let's just double check, make sure that works. Excellent. We'll just have a quick test of the scale. So currently everything is a unit vector, and we've scaled everything by 1. That's the default parameter passed through to the function. Let's say I want to make everything 5 times bigger. You can see we get a much larger ship. But it behaves in exactly the same way. We'll leave that at 1 for now. So I probably want the same thing as a model for one of my asteroids. But instead of manually defining all of the coordinates, I'm going to algorithmically do it. So I'm going to assume that each of my asteroids contains 20 points. I'll create a little for loop to iterate through them. The middle of the asteroid is assumed to be 0, 0, the origin. And each of the points are going to lie on a circle of a particular radius, which I'll say is 5. Since I've got 20 points, that effectively gives me 20 segments in my circle. And since the circle consists of 360 degrees, I want to break up my segments into degrees per segment. And so this line takes which particular point I'm on as a percentage out of all of the points and multiplies that by 2 pi. Adding the point to our model is easy. Because it's a vector, we can use the push back function. But we've got to make a pair of coordinates. And by now you should know what this is, because it's for the x-coordinate, it's radius times the sine of the angle. And for the y-coordinate, it's radius times the cos of the angle.
Isn't it great how all these things come together?
Now we've created a model of the asteroid, we need to draw it. We no longer want to draw the rectangle like we did before, so that can go. What we can do is take our player ship drawing routine, the draw wireframe model, change the model to asteroid. Want the asteroid's x location, the asteroid's y location. The asteroid's angle doesn't really matter so much at the moment, but let's take a look. Nice! We've got a circle of radius 5. Instead of scaling by specifying the radius here, I could set that to 1 to give us a unit circle. And in our draw routine, we can use the size of the space object as our scaling factor. Let's take a look. We can see it's a much larger circle now.
Right, we've done all the maths now. Let's turn this into a game.
Well, you can't have a game of asteroids without bullets. So another vector of space objects, vec bullets. Once we've updated the player's position, we'll check to see if the player has released the space key. And if they have, to the vector of bullets I'm going to push another space object. Bullets will originate at the player location, x and y. They will have a velocity of their own, which of course, the direction of which is inferred by the sine and cos of the player angle. Bullets move at high speed, so we'll set that to a high value. The size doesn't matter, and the scale doesn't matter. So just like we do with the update and draw asteroids function, we need to do the same for bullets. So I'm going to start by copying a large part of that. The bullet's position is updated by the velocity, and we need to make sure that the bullets stay within the game space. Drawing the bullet is very simple. It's a single pixel and it's white. That's the default setup for the draw command. Let's have a look. So there's some bullets and we can see them wrapping around the screen. The origin of the bullets is wherever the player starts. But I see a growing problem here. There is, of course, far too many bullets on the screen. We need to have some way of killing a bullet.
And the way I'm going to do this is any bullet that has gone off the screen is dead. We're going to remove it from the vector of bullets.
Removing off-screen bullets is made much easier with modern C. Firstly, I want to check, does the bullets vector contain any bullets? And then I'm going to use the remove if function from the algorithm library. It's part of the standard library. And it works a bit like this. It's going to return an iterator. The remove if function doesn't actually remove anything. It sorts the vector of bullets in such a way that anything that fails the if criteria is at the end of the vector. So we want to pass in some iterators to say which part of our vector of bullets do we want to inspect. Well, we want to do the whole thing. So we're going from begin to end. And now we need to pass it the criteria. And of course, being modern C, we do that with a lambda function. So my function is going to take a type space object. So in this case, actually, it's going to return true if the bullet has gone off the screen. So that way the remove if function knows to remove it from the vector. So if the x or y position of the space object is less than 1, it's off the screen, it gets removed. We also need to check against screen width and screen height. The returned iterator from the remove if function points to the start of all of the bullets which we can remove, so we'll call the erase function. But we'll make sure that there's actually something to erase first, else it'll crash. So if the iterator is not equal to the end, i.e. there is something to remove, remove it. And as you can see, now when the bullets go off the screen, they disappear. You can also see they're not destroying the asteroids, and nor is my ship crashing into any asteroids.
Time to add collision detection.
Fortunately, in asteroids, collision detection is very simple, because everything is represented by a point. So we know that the centre of the player ship is a point, and we know that the centre of a bullet, in fact a bullet is just a point, and that our asteroids are also represented by a point. So we can check all bullets against all asteroids to see, does a bullet exist within a circle defined by the asteroid's size and its central point. The same applies to the ship. And this gives the player a little bit of an advantage, because if the ship is like this with the asteroid, it's safe. However, if the ship is like this with the asteroid, the ship gets destroyed. And checking to see if a point lies within a circle is very simple indeed. We calculate the distance between the 2 points, and if it's less than the radius of the asteroid, then the point must lie within the circle. And so it becomes, if the square root ax take bx squared plus ay take by squared is less than, in this case, size, then we know a collision has occurred. Because we'll be doing a lot of collision detection, let's create a function which checks is point inside circle. And it simply takes the origin of the circle and its radius and the point, and returns true if the point lies within the circle. We'll do the collision detection when we update the bullets. Even though we're iterating through all the bullets, we'll need to also iterate through the asteroids again.
And this could cause problems if you've lots of asteroids and lots of bullets.
But for this simple little demonstration game, I think it'll be just fine. And we'll just check if is point inside the circle, we give it the asteroid's coordinates, and size, which is the radius, and we give it the bullet's coordinates. Then a collision has occurred. When we hit an asteroid, we need to do two things. The first is we need to remove the bullet. And I don't want to remove it directly from the vector we're currently iterating through. That'll cause it all to crash. But fortunately, we have a routine down here which will remove any bullets that have gone off screen. So to remove the bullet, I'm going to force it to be off screen. It'll get tidied up later on.
Each time we hit a large enough asteroid, it's going to split into two asteroids that are half the size. Now, it's no coincidence that I chose 16 to be the starting size. So when we hit that asteroid, we'll create two size 8 asteroids, and when we hit those, we'll create two size 4 asteroids. And I think 4 will be small enough, or else they'll become very difficult to hit.
So if the asteroid that's just been hit is larger than 4, we want to create two child asteroids. But I want to give the illusion that the asteroids have had some sort of impact. So I'm going to choose a random angle, and all of this is a nice way of choosing a random floating point number between 0 and 1, and then multiplying it by pi. So I'm choosing a random angle between 0 and 2 pi in this case. And I'm creating two child asteroids, so I want to do that twice. However, I don't want to do any changes to the asteroid vector because I'm currently iterating through it, and it'll crash. So I'm going to create a temporary vector outside of these two loops to store new asteroids. So any asteroids I create get added to here. And once we've come out of those 4 loops iterating through the vectors, we know it is safe to change them. So I'm going to append all of the new asteroids to the existing vector of asteroids. Now I can safely create new asteroids. So again, using my initializer format like I did at the start, we want to specify the x and y. Now, fortunately, these can be the same as the parent because it's in the same location. My random angle I now need to convert to velocity coordinates.
Here we go again. You must know this by now.
I'm going to choose some numbers. In this case, it's 10 times sine of angle. And for the y, the velocity y, it's cos of angle. I now need to specify the new size. Remember, we need to cast it to an int when we use this initializer approach, but it's easy enough because I can just bit shift it to divide it by 2. And for completeness, we'll set the angle of the space object to 0. So that's created one asteroid, and that's created another. We'll just change this angle to angle 2. But there's still one more problem. The original asteroid that's been hit is still in the vector. We need a way of removing it without corrupting the iterators. Well, we did something similar with bullets, so I'll do the same for the asteroids. If the asteroid goes off the screen, i.e. I'm going to force it to go off the screen, then it's going to get tidied up. So it's exactly the same code. In fact, I'm not going to bother checking for all edges of the screen this time, because I know that to kill an asteroid, to remove it from the game, I'm just going to set its x-coordinate to -100. So to kill the asteroid, I'm going to deliberately set its position to -100. We know it'll be cleaned up by the routine later on. Let's take a look. I've got a ship. I fire a bullet, it splits into two. And they each get a little random direction. And I can keep doing that until I've killed all the asteroids.
I suppose we best put in a way to kill the player.
Testing to see if the ship has hit an asteroid is just the same as checking the bullets. We iterate through all of the asteroids and we see is the point inside the circle, but in this time the point is the player's x and y coordinates. And if it is, we set a variable bDead to true. So I'm going to add a variable to our class. Now what do we do in the event of the player dying? Well, really, we want to reset the game. And to do this, I'm going to create a reset game function. I'm going to take some of the stuff out of the onUserCreate function, particularly the dynamic variables, so the player's location, and the vector of asteroids. I'm going to make sure there's nothing in that vector before I add to it. I'm also going to get rid of all of the bullets. And we've only got one asteroid floating around at the moment, so I'm going to add another. But I'm going to change up the starting position. And starting velocities. So it doesn't just mirror what the other asteroid is doing. We know once we've reset the game, we're no longer dead either. And because we've got the reset game function nicely and tidily starting up some game data, we'll also put that in the onUserCreate. And this shows how the onUserCreate function should be used. We're creating static resources. We're not using it to define an initial state of the game. So if I crash into this asteroid, it resets. And we'll just try that collision detection on a smaller asteroid. He says, there we go. So the player can track their progress. Let's add a score. We'll initialize that to 0, and of course we need to put that in our reset game function. The scoring system will give you some points each time you destroy an asteroid. So we need to look in our bullet and asteroid collision detection routine. We know here we've hit an asteroid, so we'll increase the score. You can have 100 points for destroying an asteroid. There's no point in keeping a score if the player doesn't know what it is, so we'll draw that in using the drawString function. But what happens when the player finishes the game? We can check for this condition by seeing if there are any asteroids left in the asteroids vector. If it is empty, then the player has destroyed all the asteroids. So that's great. Let's reward them by giving them a big score. But we'll also recreate the level. We won't use reset game. We don't want to just keep giving the same data each time. But also, we need to put the asteroids in a place that isn't on top of the player, so we don't instantly kill the player. The safest place to put some asteroids is either side of the player, offset by a set distance. So if we know in our game space, we know what our player angle is. If we take a vector that is 90 degrees to our player angle on both sides, we can place asteroids here. We know that the starting size of our asteroid is 16. So as long as we position them further than 16 away from the player, then the asteroids won't collide with the player when we put them on the game. The two new asteroids just get pushed directly into the vector of asteroids using the initializer list again. The first two parameters are the x and y coordinates, which I've chosen here to be 90 degrees, so that's pi over 2, either side of the player angle. I then set the velocity vector to have a magnitude of 10, but it's also facing in the player angle. I don't want the asteroids to start off and then immediately crash into the player. I'm going to have one asteroid go forwards, and by flipping this player angle here, I can have one move backwards.
Now for those of you that have not been put off by all of this maths, you might be thinking, well hang on, you might have just placed the asteroids outside of the game space. But that's okay, the next time the asteroids get updated, the wrap coordinates function will take care of that for us.
So now I'm just on the brink of almost cleaning up all of the asteroids, and it creates some more for us.
Our asteroids don't look very asteroidy. Let's see if we can do something about that.
When we create the asteroids, we're really just plotting a circle. And we do this by using our sine and cos functions to create all of these extra points. However, perhaps if we create these points with a plus or minus error margin, we'll get a less circular shape, but it'll be a closed polygon nonetheless. So you can imagine that gets a point there, this one here, this one there, this one here, this one here, 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 etc. And when these get drawn, we end up with a far more interesting shape. This is simply a case of changing our radius from 1 to some random number, but it's got to be a fairly well-tuned random number. I know on the whole I want my radius to be 1, but I'm going to add 0.2 margin of error, which means I need to offset it by 0.8 for the minimum distance, and it'll become 1.2 for the maximum distance. I'm also going to change the colour of the asteroid for good measure. And that's quite nice. Sort of a wobbly asteroidy thing. Since our asteroids have an angle as part of the space object, we could get them to rotate slightly, very simply. When we update the asteroid, we can modify its angle too. And we'll just pick a constant for this. And because we've put all the effort into creating a wireframe rendering engine that can take rotation matrices, it's very simple to add these sort of effects.
I could go to the effort of making sure that our bullets interact with the asteroids in a very accurate way, since they're no longer circles. But I'm not going to. I'm going to treat the asteroids as if they were circles, given that they are approximately circles, and our circle collision detection function is adequate.
I think on the whole, I'm actually quite pleased with this implementation of asteroids, and it opens up quite a number of possibilities for what we can do with the console engine now we've got the ability to render wireframe graphics.
Whew, and so there you have it, asteroids in the command line. Now I am under no illusion that this video has been more challenging than some of the others. But through implementing such a simple game, we've learned about spatial transforms, we've learned about vectors, matrices, trigonometry, kinematics, the science of motion, and we've also dabbled with a few modern C++ techniques using lambda functions and the removeIf function. Anyway, as always, all the code is available in GitHub from the links below. If you've enjoyed this video, please give me a big thumbs up, have a think about subscribing, and I'll see you next time.